this is the introduction to submodular function. Small disclaimer, it will be very light on the math side. I really want just to give you a taste of why it is important. Why, when you have something that is submodular, it's basically very great. And we will have a few proofs, very simple, but otherwise we'll keep it as simple as possible. And I'd like to start with the original problem that introduced submodular functions. Why do I do that? First, because it was published at a great year, 77. So it's a very big year, so it was important. And the title is kind of funny. Location of bank accounts to optimize float and analytical studies, blah, 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 blah. And the description of the problem is even funnier. So it is based on the fact that when you draw a check, the amount of time varies between drawing the check and the actual cashing of a check depends on the location of the bank where the city where you cash the check and the bank where the check was drawn. And if you want to do some kind of optimization, you want to ensure that your cash is actually drawn out as late as possible. And so you've got a kind of optimization problem where you want to find a location to open bank account, but are as far away as your clients as possible to be able to gain a few days and a few bucks in the process. So it's really the nemesis, the antithesis of the classical optimization problem. It is a farthest away. Yes. And so, for instance, because we've got an audience, okay, little game. Imagine that your quantum is the states of America, the 51 states of America. Okay, what will be your strategy to see if you got the problem right?
Alaska. Something like Alaska. Or Hawaii.
Or Hawaii, obviously. If you choose Hawaii, it will be far away from every other state and by a long shot. Okay, so you put something in Hawaii, and then where would you put a second bank account?
Why not all of them in Hawaii? Then people of Hawaii are going to be fast, but that's the only one.
Yes, but if you've got the possibility to open a second bank position,
you can pay people from Hawaii with the other bank account.
Yes, you're not obliged to choose. Of course. This is the funny thing.
I see. So maybe Maine or something like that.
Yes, Maine. And if you could open a third position, where would you put that?
Alaska or California?
Well, actually, the answer is
Hawaii again. The people of Maine have to go to.
The answer is nowhere. It's the sense that after you opened one position in Hawaii and one position in Maine, you cannot improve anymore your system. You've done the best you could. We can say, okay, no more Hawaii, no more Alaska. What can we say? Same question. Where would you like to put your bank accounts? Okay, I will make it short.
Washington or California, I guess?
Yes, maybe you want to do Washington and then Florida. But if you do that, the third one, probably it will be Maine. Yet, if at first you know that you will open a free bank account, maybe it's best to do Washington, Maine, and Texas. Because Texas will be able to have maybe a better coverage or anti-coverage with enough states.
So just to see if I understood, you're looking for the most distant pairs?
Yeah. Yeah. And just to illustrate this with a very simple toy model. So imagine you've got a ring of 12 cities, states, whatever, and you have a budget to open a free account in 3 cities. The delay is the distance in the ring. And so you've got the question of how to open, where to open the bank accounts. And obviously, because it is very simple. You can see that one, actually there are a couple, but one optimal solutions is just to separate by 1/3 each city where you make the accounts. So it's funny because it's optimal to minimize the distance, but it's also optimal to optimize the anti-distance. Yeah. And okay, it's optimal. And with this, the total number of days of delay for all 12 cities is 60 days, or if you prefer, 5 days per city, which is good because the maximum distance is 6, sorry. So good. And now what happens if we want to do this the greedy way? Well, if you put a city, because of symmetry, you can choose one at random. Then to optimize the second position, you want to have a great distance with the cities that are closest to the first block account. So we'll go to the diameter, opposite diameter of your starting thing. And then after that, to have a third position, basically, you will have to choose one of the side and make it in the middle to have a good coverage. And the total delay is here 59 days instead of 60. And you see why, because when you choose to have a diameter, basically you kind of forbid the solution with 1/3. And the price to pay so is 1 day. And this is actually the intention that I wanted to give you before we start. So 69 is obvious, 59 is obviously smaller than 60. So yeah, great discovery.
It's a zero.
We will prove it. So of course, when you do something greedy, it's not as efficient, but it's much easier. Basically, to have a glimpse of the optimal solution, you've got to probe all possible solutions. So this is kind of an MP problem. Whereas to be greedy, you just pick one, pick the other, very simple, very fast. And so in this time model with a ring, well, losing 1 day, it's quite acceptable. And is it a general result? We will see that it is actually a very general result. And so the early problem was to kind of maximize the delay to draw cash, to draw check. And actually, similar problems arise in many situations, both from theory and practical views. For instance, people from graph know the max cover problem. Yeah, classical problem, where basically you've got a set of subset and you want to select a few of this subset in order to maximize the onion of the subset you selected. And it's now to be difficult. And it has a real practical application. It's what is called a diversity in result. For instance, you've got a big set of documents, and each document contains some information on something or something else on some topics. And for a given budget K, you want to find K document that maximize the total information that you get. For instance, okay, I want 3 papers, only 3, but will maximize my knowledge on submodularity. What would be my best choice?
They can overlap.
Of course, otherwise it would be quite simple, but the issue is that they overlap.
Okay.
Another classical thing that is actually kind of something is clustering. So you've got a set of points, and so in this framework, you've got to select a subset of this point to minimize the distance between all the points and the subset you selected. And the subset will be actually the centers of your clusters. And so it's kind of the opposite of the bank problem we started with. And for the connoisseurs, so it is a classical problem in graph analysis to find out clusters. And so this is a kind of problem. Another, actually, it was the problem that was introduced in this network theory group by Mathieu, I think more than a decade ago. It's about early adoption. So here you are the owner of, I don't know, a new brand or a new virus, choose whatever you want as a concrete example. And you want to contaminate, sorry, to diffuse your project to the most people possible. And so it's an epidemic model. And there are multiple variants, but for instance, one of these variants is the cascade model. So basically, people can be not infected or infected. And when they get infected, one time they have a possibility to infect their neighbors according to some probability. Okay, so you've got a graph and a probability, a directed probability from node I to infect node G if I is infected, just one time. And then the problem is to which people will I give a free iPhone or something like that to be able, yes, or free virus, to be able to have the most, in expectation, the most coverage possible. Okay, and you see that there is a kind of similar color in all these problems, or maybe not, I don't know. Do they look the same for you? Yeah, good. And so now we can start to give a definition of what is a submodular thingy. So we're talking here about set functions, that is, you've got a universe, a finite universe, omega, of size n, and you want a function that give for any subset of omega a real value. And we want to capture the intuition that when you choose an item, the gain you have by choosing that item decreases with the number of items you've already picked up.
In economics, you would call that marginal utility.
Yeah. But as we will see, it can be sometimes a little bit more subtle. And another intuition that I like is that for being submodular, you cannot have combos. You know, combos, it's like, I don't know, when you play card, you have two cards that fits well, that have more powers. And the example that they usually give is a pair of shoes. So imagine that your universe is a left shoe and a right shoe. Okay, if you pick up a left shoe, the value is basically nothing. But if you pick up a left shoe while you already have a right shoe, you have a big value. So this is a combo effect, and with this, the marginal utility also have a big increase. So it is the opposite of what we want to have. Okay, and now the definitions of submodularity for a function f on sets. So you have three of them, and they are equivalent, so you can pick up any you want. So the first one is for any set S included in a set T, included in omega, and for any X outside T, the marginal utility of X when you start from S is greater than the marginal utility of X when you start from T. Did I get that right?
Yeah, exactly.
Perfect. The second definition is you've got S and T. There have absolutely no predetermined relation between them. They can overlap or not. F of S plus F of T is greater than F of the intersection plus F of the union of the opposite. And the other one is, okay, you take set S inside omega, you take two distinct outsiders, X1 and X2, and basically the marginal utility of X1 under S plus the marginal utility of X2 under S is greater than the marginal utility of X1 and X2 under S plus the value of S. No, sorry, I'm saying completely bullshit there. Oh, sorry, I go again. The function evaluated on S with X1 plus the function evaluated on S plus X2 is greater than the function evaluated of S union plus X1 and X2 and the function evaluated in S. Well, that's the formula. Okay, and
another way to say it is that the marginal utility of X1 in S is greater than the marginal utility of X1 in S union X2.
Ah, caramba, you spoiled the proof.
Sorry. A difficult proof.
Yeah. So actually, just as a wrap up, I proposed to, we don't need to spend much time, but to try to see how to prove the equivalence, because actually all the difficulties links to submodularity for the big proof is already in the proof of equivalence. So if you know how to prove the equivalence, you will have a very good glimpse of why the big theorem afterwards is true. Okay, so two, three, because it's just one. So as hypothesis, you know that if you've got x and y, the values is greater than the union plus the intersection, and you want to make this with x1 and x2. Okay, so this is a kind of easy one. Anyone wants to say?
X is S union x1 and Y is S union x2.
Yeah, exactly. Very simple, very easy. Simple one. Okay. Now, increase a little bit the difficulty. So now you've got this rule with x1 and x2, you can use it. And you want to prove that the marginal utility of x and the marginal utility with t. Okay. Any idea of to do that? And the hypothesis is, so you've got S that's included in T.
But you by recursion over you keep adding elements or
Yeah, something like that. Yeah, I know. So actually that's it. You consider the path of one path of elements that you have to add to go from S to T. And so this is where you kind of spoil the things, because if you rewrite this the other way, you just see that it's just considering the marginal difference of x under S and compare it with the marginal difference of x under S and
union something.
Union something, yes. And this you can reiterate actually, until you reach T union x minus t, f the t union x minus t, and it's all greater equal, and so you've got exactly what you wanted to show. Very simple. Last one, so that should be relatively easy. So you have the possibility to add something if you want, and you want to show that f of t plus f of t, f of s plus f of t is greater than f of the union plus f of the intersection.
Can you start from the intersection and apply what you have?
Maybe something like that, yes. So like for the previous version, you've got to choose a path. And for instance, you can choose a path from S intersection T to T. So some elements to add to go from the intersection to T. And basically, so as S and T, you will consider, I think, S under T and S. Yes, exactly. So you do this and you add the elements one by one. And so you've got a number of inequalities. So the first one is f s under t's with x1 minus f under t's greater than s union x1 minus fs. And you go from there to t, where you've got on one side t and on the other side s union t. And then you just sum all the inequalities, and all the intermediate terms will all be eliminated, and all the things that will remain will be blah 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 f of s under t union t. Don't remember. No, this one is eliminated. Oh, help me a little bit. Clack 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 clack. F the t there, f the s cap t here, and here you should have f the s union x1 and f the s union x1, or this one, sorry, f here. Yeah, got it. This one, this one, this one, and this one. These are the four that survive when you do the sums, and actually they are exactly what you want to do. Okay, so far so good. Well, actually, you know already everything you need to know about submodular functions. Yeah.
Stupid question. So far you've presented the case of a finite set.
Yeah.
But everything is more or less generalizable to infinite set, or
the issue is when you take the paths.
Yeah, that was the the root of my question.
Yeah, so actually, I believe you've got a definition. You can keep definition 1, but I'm not sure you conserve all the results. You've got a lot of tricky things. What is true is that all the definitions are not equivalent for the
Sure.
sets.
Yeah, of course.
And you have counterexamples where very strange things can happen. To be honest, I don't remember if the firm applies. Not sure.
In particular, and I'm sorry if I spoiled a bit the end of the talk, but about the approximation theorem, approximate result of the greedy algorithm. Do you need the fact that the set is finite, or? It's a good question.
Good question. Very good question. I would guess that it would work in practice, but I don't know if it has been proved. Maybe Celine will say something at the end of this.
Yeah. Celine will answer the question.
Okay, just a few additional definitions. I told you f is by default a real valued function. Sometimes you're interested in non-negative functions, so all the return functions are 0 or something positive. I didn't tell you about monotonicity, but monotonicity is not related to submodularity. So the fact that the value grows with the set, it's a property. It's an equivalent property. Sometimes you go to another property, which is symmetry. That is, if you take a set and the complementary set, the value is the same. And another property, I just mentioned it because it's very close to the submodularity, and it's subadditivity. So if you've got two non-overlapping sets, you want for them to be subadditive, that f of s plus f of t is greater than f of the union. And if you've got a submodular function, and if it's a non-negative, it is subadditive, but the converse is not true. So basically, subadditivity seems to be a nice property, but in fact, it does not. It is not strong enough to be able to make fun things. And all the things I told you about banks, clusterings, and things like that can be expressed as non-negative monotonic submodular functions. Okay, so just a little sidestep about the Maxcad problem. So Maxcad, it's another problem that interests the graph theoretists a lot. And it's NP, and it's one of the things that is used in the Louvain clustering algorithms, by the way. So you've got an undirected graph, and you want to select a subset such that the edges between that subset and its complementary are as maximal as possible. Okay. So this is the definition of a cut of a subset. It is symmetric. So it is just an example where you have something that is symmetric. It is non-monotone. And to convince you that it's non-monotone, f of empty set is 0. F of omega by symmetry is 0. But as long as you've got an edge, f of a node with at least an edge is equal of the degree of that node, which is greater than 0. So it's not monotonic. And it is submodular. Is it clear for you what it is submodular? No? Yeah? Schlick, schlick. Schlick, schlick.
Schlick, schlick.
Can you go back to the please?
To the definition of submodularity? Yeah. Yes. This is the one you want, actually, yes. With S included in T. Yeah, to be honest, the first one is the most useful. The two others are just to show off. And the full version. Yeah, sorry. Yeah.
And in the problem, what do you select? Node or edges?
Nodes. You have a subset of nodes, yes. Okay, the goal was just to make you sweat a little bit. Just show you that it's actually obvious when you know the answer. So you've got a subset of nodes, S, included in another subset of nodes. Another node U, that is external to that. When you add U to S, you will lose all edges between U and S because there were transversal edges and they become internal edges. And you will gain all other edges of U because they were purely external, and now there are bridges between U and the rest of the world. Is it clear? Yeah. And in particular, you gain whether they belong to T or not. When you add U to T, actually you lose every edges that become internal to T, which is the edges between U and S and the edges between U and the T minus S. And you gain, of course, the edges between U and the outside world. And so in the end, you've got a net loss between the two, which is twice the number of edges between U and T minus S, which is obviously positive. And by the way, this is where you can see why it is monotonic and why it does not necessarily grow with time. Because every time you add something, you lose some edges. You lose this part. And this is intuitively why, as your set is bigger and bigger, the possibility to have a net gain by adding one edge cannot diminish. But this will be another story. Okay, back to the main theorem. Yeah, I think we finished before 12. So let f be a submodular function as for let it be non-negative and let it be monotonic or monotone. I don't know what's the good word. The goal is to maximize f of s under the constraint that the size of s is at most k for some k. Okay. Usually, this is a difficult problem, but it admits an optimal solution. Let's call it S star. And now consider the following algorithm. Start with empty set. Find the element with a maximal marginal profit. Add it to your solution. Start again. Cherche the element with a maximal marginal profit, add it to your solution, etc., up to having k elements in your proposal set. And this is the value that you propose, S of k. Okay. And the big theorem for non-negative, monotonic, important negative, important monotonic submodular functions is that the value of your greedy solution is at least 1 minus 1 over E, the optimal value. And for information, the proof is kind of difficult, so I will not show it. But it's actually the best you can do theoretically, in the sense that on SP equal NP, if you want, you cannot have an approximation algorithms better with a better value than 1 minus 1 over E.
There is something I don't understand here. Where inside the text?
Where?
Oh, SK.
SK.
What is SK?
So it is the definition of a grid algorithm. Actually, I use the letters because I will use that later on. You start from the empty set, okay, and you add elements one by one. Okay, okay. So when you add one element, you get S1. After 2 elements, you get S2, S3, S4, etc., etc., etc. And SK will have k elements, and this is the value that you will propose. As this is the solution that you will propose, the greedy solution.
Okay, okay,
okay.
So where is the 1 over E coming from?
You will have a proof. So
surprise,
yeah,
surprise.
yeah. Just
sorry, there are
problems where the greedy solution is the optimal one. No?
Oh, yes, many problems. But by default, if the only information that you have that it is submodular, the problem may be, if a problem is NP-hard, for instance, almost by definition, the greedy will not be able to give you the optimal solution.
Yeah, but before you said that the greedy solution will always be to this factor 1 minus 1 over E.
At least.
It is the guarantee.
Yes. You know that the value is
the worst, it's not the best. Okay.
Yeah,
okay.
in the worst case scenario, you will have 63% of the optimal value.
What was the best? Okay.
No. And of course, in many practical cases, by chance, the greedy may find out the one optimal solution. Sometimes that's the case. In the example I gave earlier, you know, it was just by 1 day that you missed the optimal. So yeah, but you have this guarantee. It will be at least 63%, or these numbers.
A question, is this the expectation of something?
No.
No. Okay.
No, I don't think so. Yeah. It will depend on K at some point. And to prove a theorem, actually the main ingredient is this lemma. So this lemma is that if you start from any set S and you do some greedy add, you add the best possible element starting from S, the element that maximize this. The marginal profit is at least 1 over K times the difference between the value of the optimal solution and the value of S. And it is true for any set S. Some says it must be less than K, but I check the proof, actually, any set S.
Okay, so any set not necessarily included in S star.
You don't care at all.
No cardinality constraint and so on.
Yeah. Like I said, most proof give a cardinality constraint, but actually I didn't find out. Maybe you will tell me, oh, it's wrong, and we'll add. But honestly, no, I don't think you need that. Actually, you can even have situations where S has many elements, and actually its value is greater than f of S stars, but that doesn't change the fact that the lemma is true.
But you probably want to use it with S as finally.
Oh yes, in practice, this is what we do.
Yeah.
Yes, but for the lemma, it's not necessary. Okay, so the proof. How does it work? Is it very simple? Okay, we'll try to do this here with things. So you have S, any set, you have S star, and you consider the path of the difference between S star and S. It's the elements that are present in the optimal solution and that you missed for some reason. Okay, and we will work on that. So what do we do? F of F star, obviously, because of monotonicity, it's less than F of the union of S and S star. Then we will do a kind of, opposite path, tic-tac path, from F of S to F of S star union S, basically by adding the missing value 1 by 1 and say minus. So it is F of S minus F of S plus F of S union X1 minus etc. And you will rearrange to make the differences between X1, X2, X3, Xi and X1, X2, X1 minus 1 appear. Okay, it's just a rearrangement of terms. Then, ta-da, submodularity hypothesis. The smaller, the bigger. So if you consider the set S, it's included at smaller than S union something. And so by submodularity, these values are greater than these values. So F of S star is lesser than F of S plus the sum of marginal differences of the xy starting from S. But adding one element xy, it's always less efficient than adding the best element. So instead of xy, I can say that I can take the maximum value possible, the maximum marginal profit for f. So f of s star is less than f of s plus the sum over p of the maximal value. Now we remind that p is the number of elements between s star and s, the number of missing elements, and you've got less of k of them. So this is f of stars is at most f of s plus k times the marginal value. And you just have to shift the terms the other way around to have the theorem, the lemma, sorry. Okay. And you see, it's funny because you just used monotonicity there, sublinearity there, and otherwise, and you see it's same type of proof, but for the definition equivalence, you just consider a simple path and you follow the path. Okay. So, and now, well, we've got the lemma. Well, the rest is technically boring, but quite easy, actually. Sorry. So we now plug the lemma that we just showed to the greedy solutions. So S of t, just by rearranging the terms of the lemma, is at least f of, sorry, for the audience here, f of s stars over k plus 1 minus 1 over k, f of s k minus 1. And you can do recursion. You recurse, you recurse, you recurse. So I hope I didn't miss the plus 1 minus 1, but this is what you should get in the end. And then you just do a few rearrangements. So the sum, it's 1 minus the coefficient Tara power of the number of elements divided, blah, 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 blah. So it's the formula of the sum of a geometric thingy. This is here. This is where actually we leave the hypothesis that your function is non-negative to get rid of that part. Squeeze that. Okay, so we've got 1 minus 1, blah, 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 blah. This is actually 1 over k. So 1 over k divided by 1 over k. And what you get in the end is 1 minus k to the power of k times the optimal value. And this bad chance is smaller. Okay, so 1 minus x is smaller than exponential of minus x. And you've got a minus here, so minus of minus is a maxus, and it guarantees you that it is greater than 1 minus over e times the optimal solution. And this is where k disappears actually, just because 1 minus 1 over k to the power of k, basically it's 1 over a.
S star.
What?
There are maybe too many S star.
Oui, effectivement. C'est SK on the left.
Oh yeah. Sorry.
Otherwise, it would be an even more interesting result.
Yeah. My bad. Copy paste sometimes can be difficult.
What? Don't you get e to the minus k?
Well, 1 minus 1 over k is 1 minus x. So it's greater with the minus of exponential the minus 1 over k to the power of k.
Okay. Sorry.
And so exponential minus 1, which is 1 over e.
Sorry.
And so if I understood well, you can have an even better approximation if you keep the term in f of the empty set.
Yes.
And
yes, of course. And sometimes people do that.
Yeah, because if you take a submodular function and you add a very big constant to that function, it is still non-negative, monotonic, and submodular, isn't it?
Yes, but in some sense it will be cheating because all people have between 2000 and 2001.
Yes.
Okay, getting 1% approximation is very easy, but
Yeah, sure. But what I meant is that if you're in an application where nature gives you a function that is naturally like that.
Yes, of course, you can inject it, especially because this is basically 1 minus 1 over e, and
Yeah,
so
sure.
yeah, you can do that if you want. Yes, and basically that's it. This was just the basic case of submodular functions with monotonicity and non-negativity. You've got tons of variants depending of which hypothesis is right or wrong or true. So non-monotonic. You have kind of some complex constraints like the Maxcad problem can be expressed as a submodular functions if you want to. Depending on the exact use case, the approximation is never twice the same. Sometimes it's 1/3, sometimes it's 1/2, sometimes in 1/2 times 1 minus 1 over e. Really depends on the precise hypothesis that you've got to use. But the takeaway is that if you've got something that is submodular, don't hesitate to implement greedy algorithms because they will be really efficient. And the bound that are given, 1 minus 1 over e, 1 over 2, 1/3, are the usually tight bound in theory, but in practice, actually, the actual performance that you get on real data sets, it's much greater than the theoretical bounds. Because usually it's very, you have to build a counterexample to reach the bounds, basically. And that's pretty much all that I wanted to say. The rest is the sources. That's it.
Thank you very much. Questions?
Yeah.
Do you have f function, something concrete for the approximation? 1 minus 1 over e?
Good question. I need to read the counterexample paper. I didn't read the paper where they say that the bound is tight. And I don't know the kind of.
That I understand. Yeah.
I'm not even sure. So I can give you afterwards the reference if you want. I don't even know if I constraint one solution or let's just say it can, there exists solutions that are possible. I don't know. I have not this information.
It's not a question, but maybe just a comment for the audience. So besides optimization, submodularity has many interesting applications. And one of them is this correlation inequalities. It comes from the four-function theorem. And then what you say is that you have subsets of a set S, and then you have two events, A and D. And suppose both events are increasing. So if some subset is in the event A, and if superset is also in event, right? And then you look at the probability of both events. And the theorem says that they are positively correlated, because if you are in an increasing event, well, this should push the probability that the other increasing event is also true. And if one is increasing and the other is decreasing, then they are negatively correlated, because the fact that one holds seems to tend that the other holds. And this statement, which is intuitively clear, is far from trivial, and the proof uses this four-function theorem and uses this, well, it's multiplicative submodularity. F of S times of F of T is at most F of the union times F of the intersection. That's a very beautiful application of submodularity to a problem in probability that the intuition is clear, but the proof, I don't know any other proof. These are FKG 14 Castellane-Genevre inequalities. And that's a nice application of submodularity, besides this
the main one,
and optimization. So it's really a fundamental concept in combinatorics. Just a comment.
Could you have a question?
Yes. You have an example of the ring configuration earlier.
Yeah.
I was thinking if it's possible to construct this bound using this ring example.
I believe a ring is too simple to reach the bound. My intuition there is no. If you want to build the bond, you've got to really craft the values of each subset very precisely.
Probably some instances of max cover should be enough, I guess.
Yeah.
Max cover, I think, is sufficiently general to
reach the bound.
To be able to be shitty enough.
Yeah. So the ring is not enough, but yes, maybe you're right. Max cover is kind of
a good candidate.
Yeah.
One piece of information also says also to Ethan has written a very interesting book on the use of submodular functions for queuing theory. So it's also fundamental. So actually, the results in queuing theory, queues are sort of convex dynamics, and so you also want for input point processing or things like that to find the most regular one.
Yeah.
And so there were several research actions, and so really the breakthrough was the use of submodularity. So Bruno Gojal, Ethan Altman, and there was somebody in the Netherlands. But so there were a series of papers, and they wrote a monograph on the
use of submodular functions.
Yeah, because initially the one who found the ideas was Bruce in the US. And they extended, so they looked at, for instance, Maxcad dynamics, linear dynamics, higher dimension. They proved lots of results on the optimal input. So it was neat to, for instance, when you have queues for routing, the set is the subset of a point process where you will route. So you have two queues. And the initial point process, and you want to have an open loop routing mechanism, which is blind, doesn't know what anything, and tries to minimize the maximum load in the two queues by choosing sets, subsets of the set of point process. Single input one. So it's really the routing, and this is a sort of open loop optimal solutions, blind thing. And the tool to solve these problems in a very complex, so convex dynamics like this Maxwell's ones, they solved all these problems using this notion. It's mind-blowing. It's very powerful.
I also have a question. So here you describe the greedy algorithm where you start from the empty set and then you add elements X greedily. But you could also imagine that you start from the complete set and then you remove elements until you reach a subset of size K. And each time you remove an element, you try to decrease at as less as possible the value of F. And have you heard of results about these other?
It probably exists. I don't know because sometimes you have to be very careful of the sign. Maybe it's minimization. So it has to be checked thoroughly. What I know of is you have some techniques where, for instance, you try to find, say, okay, K is difficult, but a small k is easy. So you've got some solutions where you try to find like the best solution with a small value of key, and then greedily you kind of pack the rest of things together. The other way around, I don't know. What I can say is that for non-monitoring function, like the Maxcad, it's very classical to actually try to explore by adding and removing edges. Because from Maxcad, because it's symmetric and non-monotonic, you can have gain by removing edges. So I know that the algorithm tries to explore by adding and removing partly until it reaches local maximum. But I don't know. I don't know about the simple guess.
So when you look at more specific structures, say you're on Z2 or something, and take the integer points, right? So what is the connection between submodularity and concavity, or directional concavity? So,
in terms of cardinality?
Yeah, so I mean, it has clearly, I mean, submodularity is linked with concavity, right? And so assume your set is Z2. Is it enough to have, so what is the connection between the locality Z2 and submodular? So my question is, so for instance,
well, the issue is I don't see what will be concavity. It's for a function of the element of Z2, whereas submodularity is will be the subset of Z2, and I kind of struggle to patch the subset. So it's always omega versus 2 to the power of omega. It's not very easy to match them together. So sorry, I can't give you a simple answer there.